Hey everybody, Dr. Retzik here. This is our second video in section 7C on positive operators. Let's get started. So far for positive operators, we've established a bunch of things that are equivalent to being positive. So remember, here's our setup. You have an inner product space V. You got an operator T. Inputs from V, outputs in V. And what we established in 7.35, I think that's the theorem name, 7.35 is T is positive if and only if T is self-adjoint and all eigenvalues lambda are bigger than or equal to 0, if and only if T has a positive square root R, if and only if T has a self-adjoint square root, if and only if there exists an operator R on V such that T is R star R. Okay, so we have a bunch of things that are true and are all equivalent to T being a positive operator. Now, these words here in that statement bear further discussion. So being positive means you have a positive square root. Now, we actually know what that is. Namely, it's the operator whose matrix is just root lambdas down the diagonal, where those lambdas are the eigenvalues of original T and zeros everywhere else. That's the operator in the proof of this statement that justifies that part of the theorem. So that is a positive square root of R. If you do that operator twice in a row, you just, or positive square root of T, excuse me. If you do that operator twice in a row, you just get T. Okay. Our next result tells us that that R right there, the one with the root lambdas down the diagonal, is the only positive square root of T. So in 7.35, you find out that T has a positive square root. In 7.36, you find out it's unique. Okay, so this is result 7.36. And if then, it says if T, a linear operator on V, is positive, then T has a unique positive square root. Okay, so think about the structure of how we're going to prove this. We already know it has one, this one. So to prove that that's unique, we're just going to argue, okay, well, let R be any positive square root. Maybe that one, maybe not that one. And then we're going to show, no, it's that one. And to show that it's that one, all we have to do is show that this mythical R does exactly the right thing in each column of its matrix. So all we're going to do is we're going to say, all right, let T be positive. Oops. Let T, a linear operator on V, be positive. Okay. Then T is self-adjoint. And by spectral theorem, there exists orthonormal basis E1 through En with eigenvalues lambda j all bigger than or equal to 0. Okay, so you have this orthonormal basis that's working. It consists of eigenvectors for T with corresponding eigenvalues all bigger than or equal to 0. Okay, so E1 through En are in there, and that's how they work. Okay, what we'd like to show is that any positive square root for T does the exact same thing to each of those E's. Okay, so here's our idea. Show that any positive square root R of T satisfies R acting on EJ is root lambda j EJ, and that's for each j 1 to n. If we can show that, then we will have shown that this blue matrix here, that is the only thing that R could be, and therefore R is unique. Okay, so that's our job. Okay, so here's what we're going to do. Let's focus on a particular column of that matrix. So let's take a j somewhere between 1 and n. So let j be an element of 1 through n. So that's us focusing on a column of our matrix. Okay, and let R, comma, and let R be a positive square root of T. We know there's at least one, and now we're just letting R be an arbitrary positive square root of T, and we're going to show that R, in fact, does this. Okay, well, here we go. Since R is positive, that means R is self-adjoint, And that means there's an orthonormal basis of eigenvectors for R. Okay, so let's write that down. Then spectral theorem gives ON basis F1 through Fn Shh. No. Shh. Shh. The spectral theorem applied to R gives an orthonormal basis F1 through Fn such that R acting on any particular Fi is equal to alpha I Fi, where each alpha I is bigger than or equal to 0. This is because R is positive itself by supposition. Okay, fantastic. So in our diagram up here, not only do you have E1 through En that are a nice orthonormal basis of eigenvectors of T, but you also have lurking up here F1 through Fn, a nice orthonormal basis of eigenvectors of R. Okay, but they're both bases. So for the J we're interested in, it's possible to express basis vector Ej as some combination of the Fs. So Ej equals A1 F1 plus dot 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 AN Fn where the AI are just scalars. Okay, well hang on though. If that's Ej, then R acting on Ej, well remember what the Fs are. The Fs are eigenvectors for R. So when R acts on Ej, R acts on each of those terms, A1 F1 plus dot 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 AN Fn, and that gives A1 alpha 1 F1 plus dot 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 AN alpha N Fn. Okay. And if R acts on that, then R squared acting on Ej is A1 alpha 1 squared F1 plus dot 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 AN alpha N squared Fn. But wait a sec, wait. R is a square root of T. So R squared is T. So this is T acting on Ej. Okay, wait, hang on though. Remember what the E's were. The E's were eigenvectors for T. So T acting on Ej, what was that? It was lambda J Ej. Okay, wait, but hang on. What was Ej? Ej was that combination of the Fs. So in fact, this is lambda J times A1 F1 plus dot 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 all the way through AN Fn. Okay, all right, let's focus for a second here. So that means this quantity which is r squared acting on EJ, is the same as this quantity. Which is T acting on EJ. If you set those two equal to each other, and then move everything to the left-hand side, then I think we're here. Thus, okay, we're going to have some big combination of the f's coming out to 0. So what's that combination going to be? It's going to be, on the left-hand side, you already have an a1 lambda 1 squared, and then you're going to subtract over to the left-hand side a1 lambda j. So I think we're here. Alpha 1 squared minus lambda j, all times f1 plus dot dot dot, and then all the way through an alpha n squared minus lambda j fn, and all that equals 0. Okay, well, let's keep our bearings here. What were the f's? Scroll all the way up. What were the f's? The f's were a basis of eigenvectors for R. So in particular, they're linearly independent, which means each of these quantities is 0. Okay, each of those quantities is 0. Now, a given one of those red underlined quantities, those coefficients, could be 0 for one of two reasons. Either it's the A's fault, so maybe A1 is 0, or it's the parenthetical term's fault. So it's either this one's fault, or else it's this one's fault. Okay, so it is really possible that some of the A's are 0. But if some of the A's are 0, then we didn't need to write them up here in the first place. So whichever of those A's is 0, we could have left them off way up there when we described EJ in terms of the F's. Okay, so basically what I'm trying to say is, in retrospect, we know that EJ is definitely a combination of the F's. So let's say AI, Fi. But we really only need the combination involving AIs that are non-zero. So EJ, that one eigenvector for T, can be written as a combination of the F's, the basis of eigenvectors for R, and we may as well not use any pieces of that combination where the coefficient is 0. So that's what we're writing right there. So it's the sum of all the AI FIs, but we're only going to look at the sum over the indexes I, where the coefficient AI is non-zero. Okay, but hang on. We just said every one of those red underlines is 0. So if AI isn't 0, then this is the combination of the F's where alpha I squared is lambda j. So EJ is the combination of the F's over all the indices where alpha I squared comes out to that lambda j. Okay. So then R acting on EJ. What is R acting on EJ? Well, it's acting on that combination. It's a linear operator. So this is the sum over all the indices where alpha I squared is lambda j. A sub I, and now R acting on Fi. What is R acting on Fi? Keep all these different symbols and subscripts straight. The Fi's were eigenvectors for R. So R acting on Fi, that is alpha I Fi. But in this sum, alpha I squared is lambda j. Alpha I squared is lambda j. In other words, alpha I is root lambda j. That lambda j is fixed. Pull root lambda j out in front of the sum. You're left with AI Fi on the inside, and this sum right here is this sum right here is equal to EJ. And that's the end of the proof, because we've achieved this goal. Right here is what we set out to do. We set out to show that any positive square root R would have to act the same way on each of the E's. And the whole rest of the proof was us taking an arbitrary EJ, some positive square root of t called R, and in the end, we showed R has no choice but to act on EJ in that way. So not only do you have 7.35 that tells you, oh yeah, there's definitely a positive square root, like this matrix here, this one. Yeah, not only is that a positive square root, it's the only positive square root. That is literally the only operator whose square is t and which is positive. Okay, so zoom way out. Lots of technical detail in there. You had two different orthonormal bases going, but zoom way out. What really happened there is we enhanced 7.35 by saying, hey, remember that positive square root you showed existed in 7.35? Well, it's unique. It's the only positive square root. And that's 7.36. Okay, on to isometries next. See you next time.